Good evening, ladies and gents. Let's talk a little bit about solving triangles using trigonometry. Now, trigonometry, if you think about the word, literally means the study of the measurement of triangles. And that's all we're doing here. Now, the thing we're going to focus on is the skill. Like, how do you actually solve a triangle using this methodology? But we can't lose sight of the fact that the whole thing is built on similar triangles. Now, we spent a lot of time talking about ratios of similar triangles, and I don't want you guys to lose sight of the fact that this is the idea upon which it's all built. The difference is, though, even though we may take like a similar triangle, what we're going to call a reference triangle, and compare it to a triangle down here, the thing we're not going to do is use our old methodology, particularly using k-factors. Now, I do know this is a good method given the information you currently have. But one thing I want to try to convince you of is one, like what you're going to see works, but two, also the K factor is just something you got to put out of our heads. Like that's okay to do in the realm of pure similarity, but in trigonometry, that's not a methodology that is going to work for very long. It works right now, but really in the course of the next couple of weeks, you're going to see hopefully that methodology does. But anyway, let's just jump right into it. So I'm going to square a couple examples. This is not the homework you had before the green sheet, but this could very well be a homework you have in the future. At the very least, it's just a couple examples. So let's go to start with this one. So we're trying to solve this triangle, and so what that means is we're trying to find all the pieces that we don't currently know. There's a couple obstacles in our path. One, we have an angle defined in radians. Not a huge deal, but we're going to have to at some point work that out. Two, I have a lot of things here that I don't already know. So the way I'm going to start this problem is first to actually choose the angle which I'm going to orient the triangle with. In other words, choose what I'm going to call a referencing angle. So for me, it's going to be this pi over 6 angle. Even though it's defined in radians, a quick conversion can get that to degrees. The reason it's important to define the reference angle first is so that you can then, identify the other pieces of the other triangles. And so if we're standing here and this is my reference angle, I'm going to call this guy OP, which is going to stand for opposite, and this guy is going to be A, which is going to stand for adjacent. I already know the hypotenuse, so these are the two things I have to find. This angle should also be named, I'm going to call it alpha. Ooh, I'm going to call it alpha. Just you can call it whatever you'd like. Those are just the things I'd like to call it. So if I'm going to have a hope of finding any of this stuff, I'm first going to have to understand what pi over 6 in radians means in degrees. Even though radians are the preferred thing to work with in upper level math, it's not something that we're used to orienting ourselves with right now. And so our first job is to figure out what pi over 6 degrees actually means. Now we do have this conversion. We know that pi is equal to 180 degrees, and we can use that a couple different ways. The most straightforward way is probably to use it maybe in a ratio, but we can also use it as a substitution. And so if we know that we have pi over 6 radians, knowing that pi is the same thing as 180, we can take this to also mean 180 degrees over 6. Now this only works if you're using radians to degrees. It's really hard to use this method backwards. Going backwards from degrees to radians, you probably want to use like a ratio defined method, but this is okay for now. So pi over 6 in this case would be 180 divided by 6, which would be equivalent to 30 degrees. And so pi over 6 is actually equal to 30 degrees. Now right away we can tell the value of alpha then. This is going to have to be 60 degrees. And so we're 1/3 of the way done with our work. We know that the angle is going to be, the other angle, alpha, is going to be 60 degrees. Now what we have to do is to solve for OP and solve for A. I suggest strongly that you use the structure we gave you in class. It's a couple different reasons for this. One, will keep you organized. Two, is going to make the transition away from K-factor a whole lot easier. So if you recall what that method was, or the structure was, is really a three-part thing. The first thing is to pick the angle of reference, which we just did. The second is to acknowledge that we're comparing two triangles. And so organizational sakes, what I'm going to do is designate this side my reference triangle side. And then over here, let me change colors. This is going to be my actual triangle side. Okay. Now the relationship between these triangles, the reference and the actual, is that they happen to be similar. What I mean is, if we have a hope of solving this actual triangle down here, we're going to have to find a reference triangle up here that is similar to it. If they're similar, then they're going to have the same ratio. If they have the same ratio, we're going to be able to solve it. So hopefully I'm going to try to find an angle or a triangle that has a 30-degree angle in it. It turns out I have one actually right here. And so this guy will serve to be our referencing triangle. Now, writing this first ensures the grader, your teacher, that you guys understand this does come from a similar triangle relationship. Now, the next step is we have to figure out which side lengths we're going to actually solve for. Now, we can't do both at the same time, so we're going to have to pick one. And just for the sake of argument, let's go ahead and solve for A here. So now in this triangle, I have to know what other piece I have to work with. Well, I was given the hypotenuse, and so this is going to form my ratio that I'm going to use in comparison to solve. I have the adjacent side, I have the hypotenuse side, and I'm using the 30-degree angle to orient myself as a reference angle. So the next thing I'm going to write is actually that ratio. So before jumping with numbers, what I'm instead going to write is that I'm going to compare the A over H ratio using a 30-degree angle to the A over H ratio of my actual triangle, also using a 30-degree angle. Now, because these are similar, the triangles themselves are similar, I know that these ratios should be the same. Again, this is a step that we want to actually see in the work. Okay? This is for a couple reasons. One, again, it communicates to your teachers that you know what you were doing. And two, it gives you a chance to fix your work later much easier if indeed you do make a mistake. So from this point forward, now what we're doing is actually just pulling the numbers. So in my actual triangle, the one that I have in front of me that I'm trying to solve, the A side from the reference angle of 30 degrees is going to be still A, it's this guy right here, but the H is going to be 10. Now, seeing that these are similar triangles, I know that these ratios should be the same, and so I just need to pull the A over H ratio for my reference triangle. Well, using 30 as my reference, the adjacent is 0.8660, and the hypotenuse is 1. And so we can get those into a ratio, 0.8660, and then 1 is my other one. Now from here, it just turns into a purely algebraic exercise. Now I know the ratios are the same because they're similar. I pull those, keeping the work completely separate left and right. All we have to do is now do a little cross multiplying and solving for A. So cross multiplying this way, A's will just be A. It's 1A, but we know we don't need that. And then we have 0.8660 times 10. 0.8660 times 10 just moves the decimal point once, and so we have 8.660. Okay, and that should be my value for A. Now before we move on, we should do a couple things. We can put that here just for visual. But we should also take an opportunity to ask ourselves if that even makes sense as a number. Given the hinge theorem, we know that if you have an angle, the largest angle should be across from the largest side. So we know 10 has to be the largest side. That's actually why the hypotenuse is the largest. It's not just some arbitrary rule. It's because it's across from the biggest angle. So 8.660 is smaller than 10. That makes sense because it's across from the 60-degree angle, which is less than 90. Okay, and so now we can move on and we can now solve for, let's see, we can now solve for the other angle, in this case, our other side, OP. So I'm going to start this in a very similar way. First I'm going to designate like a reference triangle side, and I'll designate an actual triangle side just to orient myself. I'm also going to remind myself that these are similar triangles, so I'll go ahead and put in that structure as well. Now I'm going to need to pick a ratio and a reference angle. I'm going to use 30 again, but now I'm dealing with OP. Now I could use A as part of my ratio. I wouldn't, simply because, like, what if I made a mistake with A? Like, I feel confident we did it right, but you never know. So I think I'm going to use H again as well. So I have H and O, I have the opposite and hypotenuse side. So it doesn't matter how I write this ratio because we know ratios are reversible. So I'm going to go H over O using my 30-degree angle as a reference, and that should be the same as H over O in comparison using the same angle of 30. Now, since the triangles are similar, these should be equal. Okay? And again, we're writing this out as an organizational step for you and also a confidence step for your teacher that you got through this knowing the idea behind it is triangle similarity. Okay? So now our job is to start pulling actual numbers. So for our actual triangle, the one we're dealing with, the hypotenuse is 10, so I can write down 10 here. And the opposite side we're calling OP. Okay? So now we need to also compare that to the ratio of our reference triangle. Luckily, we're using the same reference angle, so we don't have to worry about that. We just need to pull the hypotenuse and the opposite. So it looks like we have opposite and hypotenuse. So the hypotenuse is 1, the opposite is 0.5000. Okay? And then zooming back in, again, there's still similar ratios or similar triangles. So those are going to be equal ratios. Now let's go into our algebraic solving step. Boom, boom. So OP, the opposite side, is equal to 10 times 0.5000. And again, a multiplication by 10 is pretty straightforward. It's just going to be 5.000. Okay. So again, before moving on, this now we know this is 5.000, just 5. We should take a second to make sure these side lengths actually make sense. So again, given the hinge theorem, biggest angle across some biggest side. So we could note that 60 is bigger than 30, and so A should be larger than OP. And it certainly is. 8.660 is certainly larger than 5. Okay. Now, if we really wanted to check it, we could go into the Pythagorean theorem and check these three values one against the other. Like we know, since it's a right triangle, a squared plus b squared equals c squared. And so I have this calculator off screen, but I can check 8.660 squared plus 5 squared is 25, equals about 100. It's 99.9956, which given human error and rounding, that should practically 100. And of course, 10 squared, c squared is 102. And so those are two ways you can check your work without actually needing a key. You can just kind of think, one, about the hinge theorem to think of the things that actually line up well, and two, actually try the Pythagorean theorem. Like, you should never turn in one of these incorrectly for that reason, okay? If that was good for you and you kind of understand the rhythm and like the structure that we want, that should be good for this video. I'm going to go ahead and do another example really quick. And so if you want to stick around for that, you're welcome to. But it's going to be a repeat of what you just saw, just with different numbers and different values. Okay. So that was good for you. Thank you. Thank you for taking notes and doing what you should do to keep caught up in class. If you want to see another example, keep watching the video. So let's go. So we're going to do the same thing first. The first choice I'm going to make is what reference angle I'm going to use to orient myself in this problem. Just to be no surprise, I'm going to choose the one that I was given, which is pi over 9, which means I probably need to do a little work about converting this to a degree measurement so I can kind of communicate in practical terms. Once again, I'm going to use the fact that pi is equal to 180 degrees, and since I'm doing conversion from radians, I can actually just do this as a substitution. So pi is actually equal to 180 divided by 9, so that's going to be a 20-degree angle. And so this guy is actually 20 degrees. Okay. So I'm going to use that as my reference angle. It's also going to be what I'm going to use to help me find the value of the other guy. Let's see. So this guy right here. Because if that is 20, then this definitely has to be 70 degrees. And now I have my two angles. So now I can focus on the sides. Referencing from my 20-degree angle, this guy right here, I'm going to call H for hypotenuse, and I'll call the bottom A for adjacent. A little unimaginative, but it helps me keep the pieces right. So identified 20 as my reference angle to keep everything in the problem nice and straight. Identify the two sides using variables, in this case H and A, and now we go about solving. So again, I'm going to do the organizational step first. Again, this is something we want you to see. I want you guys to do for the time being. At some point, you'll definitely be able to drop it. But for now, we do want to see you separating the two sides of your paper, two sides of your work, as in reference angle, a reference triangle, excuse me, an actual triangle. And please acknowledge that you know the relationship here is similarity. So now we can go into solving. It doesn't matter which one we solve for first. Let's just solve for H first. And so we have to choose something other than H to help write a ratio. And so the only other value I have is 14, so that's the 2 I'm going to use. Now 14 is the opposite side, and so I have to write opposite and hypotenuse in a ratio. I'm just going to go O over H. Now I do want to also acknowledge what the reference angle is that I'm using, and that should be 20. Okay? So that's the ratio I'm picking to use to solve. Using a 20-degree angle as a reference, I'm using the opposite side and hypotenuse. Now, since these are similar triangles, they have to be compared to the same ratio, and so I'll just write that again, but for my actual triangle. A little tedious, sure, but it's going to help us keep you organized and ensure that you know what you're doing and not just kind of guessing numbers. Students who do this extra step are 80% more likely to actually get the problem right. That's just historical fact. So let's actually get into the writing pieces. So let's go to the actual triangle. The opposite side from 20 is actually 14. And then H is what we're solving for, so we'll stay a variable. That's going to be equal to the same ratio, but in the reference triangle picked above. And so let's go to reference triangles. We're looking for a triangle with a 20-degree angle and known side lengths to solve. Okay. In the first glance, I don't think I see one. So if you notice all the angles given, that's 15, 50, 65, 30, 45, 10, 35. But if we look here, even though it's not explicitly marked, we know if that's 70, this has to be 20. So this is actually the reference angle, or reference triangle, excuse me, that we're going to be using. So there's something to look out for. If you, even though you pick 20 as your reference, doesn't mean you're necessarily going to be given one that's explicitly listed as 20. And so you have to be clever and make sure that you're not getting tricked by something like that. Now, if you recall, the two things we need are hypotenuse and opposite. And so from the 20-degree angle, the hypotenuse in this case is 1. The opposite is 0.3420. And so we can get that right back here into our referencing values here. So 0.3420, and then my hypotenuse is 1. Let's do a quick double check. Let's see. Opposite 0.3420, 3420, and then the hypotenuse is 1. If you notice, all the hypotenuses have been 1. There's a reason for that. There's a practical reason for it. There's also a mathematical reason for it. That's something we'll get in later in class. But for now, let's go ahead and carry out the algebra. Let's go ahead and cross multiply. So one way I have 14. The other way I have h times 0.3420. I'm going to go ahead and solve for h only. So let's divide by 0.3420, divide by 0.3420. And so that tells me if I want the value of h, I'm going to have to take 14 divided by 0.3420, which I can do off screen here. 0, oops. Hey, I got 40 point, oops, back up there. I got 40, and I'm going to carry this out to 3 decimals, 9357. Okay, now that's a large number. So before we accept or reject it, we should take a look back at our triangle and just ask ourselves if that's even reasonable. And given our triangle and that's hypotenuse, it definitely seems like that's okay. We won't really know until we find a, but it's certainly larger than 14, which is something we expect from the Hinge theorem. The hypotenuse should carry the largest side. And so before we pass away judgments on that, let's go ahead and solve for a. And so I'm going to start with the same setup I had before. I'll first start by designating a reference angle side, or reference triangle side, excuse me, and an actual triangle side. Okay. Remember the relationship here is similarity, and so that should bore for us 2 equal ratios. Now we are trying to solve for a here, the adjacent side, still using 20 as our reference, and so we're probably going to use opposite this time to help us. So let's go opposite over adjacent. We could go the other way. I'm just feeling opposite over adjacent today for some reason using that 20-degree angle. Because they're similar triangles, the ratios have to match, opposite over adjacent for 20. And so now let's start pulling values. So the actual value, going to the triangle I am trying to solve here, the actual value of over a happens to be 14, and then a. And then let's go to a triangle. We need over a for our referencing triangle. Still using the 20.3420, of course, for the opposite, 9397 for the adjacent. Okay. And so those were born right off our reference triangle, opposite being 0.3420, adjacent being 0.9397. We can double check our literal equation above. We should be O over A, so everything looks pretty good. Let's go ahead and rock the algebra. So we're going to do cross multiply here. So A times 0.3420 is the same as 14 times 0.9397. And again, instead of doing 2 calculator operations, I'm just going to go ahead and solve for A here. So I'll divide by 0.3420, divide by 0.3420, and that way I can just enter everything in my calculator at one time. And so the A value should be approximately equal to, and I'll do this off screen, 14 times 0.9397, and then take that result, divide by 0.3420. Now, before I run this, we should take a look over here. Oops. Well, you take a look over here. Now, if we look at A, that's across from the 70-degree angle. Okay, so that number should be definitely larger than 14, but it should be less than 40.97, the hypotenuse. And when I ran that, what I did get was actually 38.467. Let's go to 473. Right? And so it falls definitely within our parameters. So that's what we expected. We expected a number that's larger than 14 but less than 40, and we got it. If we can check this by the Pythagorean theorem, but I have a strong suspicion that this is going to work out just fine. If we take 14 squared, which is 196, add to 38.4673 squared, that's equal to about 1676. If we take 40 and 0.9357 and square it, again we have about 1676. And so checking with the Pythagorean theorem, rather than saying logically through our hinge theorem, we're going to actually be able to check our results before moving, or without actually knowing what the numbers are, like with a key. Okay. Guys, so that's it. That's just solving in a nutshell, at least at this level. We're going to be changing the game, evolving and sophisticating our techniques as we go. But for right now, that's what we're looking for you to be able to do. The big steps, the things that we're going to want to see all the time, are going to be these first two steps, are really the first three. If you can get it to these first three steps flawlessly, you're not only going to be earning most of your points, you're giving yourself a chance to make sure you understand the idea behind trigonometry, excuse me, and not just the action of it. Okay? In other words, this is what's being rewarded with the most value. Everything else is just a couple algebra steps. If you look, like after what I've highlighted, it's only a couple things to do. Is cross, multiply, divide, and solve. So if you can give me these first three steps, that's going to get you the most value, the most bang for your buck. Honestly, the most points too, right? So that's what I have for solving. Thank you so much for taking notes and making sure you know how to do this. That's all I have for you. Thanks.